Hello everybody, welcome to another day in the barn. Hope everybody is doing well and we're ready to get into another new week. Okay, so today we are looking into chapter 3. So chapter 3 is going to be some uses of the derivative. Okay, where does it help us? How do we use it? So we'll get right into that. Now, 3.1 and 3.2, they have them split as separate sections, but I don't really like the flow that they use, so I'm going to kind of do this together. So 3.1 and 3.2 together, okay? So 3.1 slash 3.2. I don't like that pen. Let's see what we got going on here. And what we're looking at is increasing and decreasing. Okay, so we know that the derivative tells us the slope of a tangent line. Now, if that tangent line, so let's say we were to draw just a little sketch here. If that tangent line has a positive slope, like this one does, notice how the graph, not the tangent line, but the graph itself happens to be increasing. Now over here, if we were to draw in this tangent line, okay, notice how the tangent line would have a negative slope, right? And the graph seems to be decreasing. It's going down at that point. So we're going to use this idea of the tangent line and the slope of the tangent line to be able to tell us what's happening in the graph, even if it's some graph that we really don't want to graph, that's really ugly to graph. We can tell just by looking at the derivative. Okay, so here we have the kind of definition here. This says, if f is differentiable on the interval a to b, open interval for this, then first it says if the derivative is greater than 0 on AB, then the function is increasing. Then f of x is increasing. Second one says, if f prime of x, so if the derivative is less than 0, okay, so negative on the interval AB, then the function f of x, the original function, is decreasing. And third, if the derivative is equal to 0 on an interval a to b, then the original function is constant. That doesn't happen very often, but it could, okay? So basically, again, what we're looking at is that derivative is going to tell us what's going on, whether we have an increasing function or a decreasing function and where it's happening. So as a very small example, just so you can see what we're doing here, let's just use our very basic f of x equals x squared. Now the nice thing about this one is that we know what the answer should look like before we even start, okay? So, you know, we've got our graph over here of just our basic parabola. And we know that if you're going from left to right, that this is decreasing and then it turns to increasing. So remember, it's always left to right. Don't do it like from the middle or anything. So from left to right, this is decreasing and then the graph turns around and starts increasing, okay? So let's see how the function itself is going to teach us that. So first we find the derivative, which is just 2x. Okay. Now that doesn't necessarily tell us where things are positive or negative yet. Okay, again, we've got our graph, but we can't really tell just from this. So we want to come up to here. And what I want to ask you is that for a graph to be, or sorry, not a graph, for the derivative to be greater than 0, and then for the derivative to be less than 0. To go back and forth, what do they have to do in between? Okay. Don't they have to reach 0 so that they can flip to the other way? So what we want to do now is we want to figure out where that change is. Okay? So where is the derivative equal to 0? So the next step would be to take this and set it equal to 0. So we get that x equals 0. Now, the common way for answering this question is on these little intervals. So it's very important that we write out these little intervals. So what we're going to do is we're going to discuss this side of the graph. And that interval starts way over at negative infinity. And it comes all the way up to 0, doesn't it? And the next interval starts at 0, okay, open bracket, starts at 0, and continues on towards positive infinity. Okay, so now what we're going to do is we're going to decide whether the derivative is positive or negative. So f prime of x. So what we want to do is we want to take any number that's in this interval here, okay, and stick it into our derivative, not the original, into the derivative. So like -3. So we could find f prime of -3, which will be 2 times -3, which is -6. So we don't really care about the negative. What we care about is we don't really care about the 6. What we care about is the negative. So if you want to put -6 there, you can, or you can just stick the negative sign there. Now, we're going to take a number from this interval, let's say positive 2, and plug it into the derivative. And we end up with a positive 4. But again, 4 not as important as the positive sign. So we've decided, not from the graph, but from the interval and the derivative, okay, from the interval and the derivative, that it's negative, the derivative is negative from negative infinity to 0, and positive from 0 to infinity. So that means we can do like one more column here that will tell whether we are increasing or decreasing. So that means, since this was negative, this interval is decreasing, and this interval is increasing. So this is kind of the normal setup for answering this. Okay, so you're going to notice in your homework and everything, it's going to say discuss areas of increasing and decreasing. Discussing means drawing this little table. Okay, you don't have to like write a whole paragraph or anything like that. It just means writing this little table. Okay, so that's what we're gonna get in doing more of that. But before we do, let's go back to what we're talking about here. We said that when we found the derivative, you know, we can see that it's decreasing and then increasing, but at this point, something special was happening. It's where we flipped from decreasing to increasing. And because that point is special, it gets its own special name. Okay? So let's erase this part here. So that point is called a critical value. So let's talk about the critical values. Okay, so this says C is a critical value for the function f when f prime of c equals 0, okay, so where the derivative is 0, which is what we got in this one, or f prime of c is undefined, or f of c is undefined. Okay. So remember that the idea here is that these are called critical values. Critical values mean something special or critical is happening to the function or to the graph. So we said one thing that is critical is where we get that horizontal tangent, where the derivative equals 0, we're going to get a change going on there. So that's that first one, okay? And that's what we're normally looking at. But there are two other ways that we find critical values. And critical values would be where the function or its derivative are undefined. So as another simple example here, we're going to use our most basic rational function of f of x equals 1 over x. And this guy looks like this. And there is a vertical asymptote here at the y-axis like that. Okay. So in this case, what we're noticing is the function itself is undefined when x equals 0, or we'd say x can't equal 0, right? Well, that would make 0 a critical value. So x equals 0 is a critical value. Now, again, there's nothing going on in the function at that point, but does something critical happen? Is there a definite change in the graph? So at 0, the graph goes from being down here to being up here. So the critical values can be, again, where we change from increasing to decreasing or decreasing to increasing, or they can be things like an asymptote or a hole or a jump. Okay, so where something special is happening in the graph. So where something special is happening, that's going to be a critical value. So let's practice a little bit with critical values here. So let's say that they gave you g of x is x squared minus x. And they just want us to find critical values. And you'll notice they abbreviate those CV there. Okie dokie. So it's a polynomial to start with, which means it's not going to have any places where it's undefined or discontinuous. So there's nothing special in that sense. So basically when we look for our critical value, we're just looking for where the derivative equals 0. So we're going to find the derivative here. So g prime of x equals 2x minus 1. And then we want to figure out where something special is happening. So we're going to set that 2x minus 1 equal to 0. Okay. And slide everything over, and we get x equals 1/2. Okay. So this graph has one critical value at x equals 1/2. All right, let's look at another one. I'll leave that for a second. Okie dokie. So what if f of x equals x to the 4th plus 1 over x squared? Okay, and again, we're just looking to find critical values. We're not doing anything more. But when you look at this guy, we're not looking at a polynomial anymore, are we? So the fact that we have a rational function means that there's going to be a critical value right off the bat where x equals 0. Does everybody agree? Because that's where we're going to have a discontinuity or an asymptote in the denominator. Okay, so we can say right off the bat, so critical value, boop, x equals 0. Now that doesn't mean it's the only critical value, it just means it's one of them. So we still have to find the derivative and see how the rest of this goes. So we find the derivative, and let's go ahead and practice. So if we were to do this, looking at intervals, make sure you put them in the right order. So the first interval is going to go from negative infinity to negative 1. Negative infinity to negative 1. Then the second one is going to go from negative 1 to 0. Then the third one will go from 0 to 1. And then there's one more from 1 to positive infinity. Oh, that was unfortunate. I just erased our derivative. But shoot, oh well, we can figure it out. Okay, so let's say that we are going to do our derivative here. And remember, we're just trying to decide whether things are positive or negative. So let's say that you take a number that's in this first interval, so a negative number like -2, and we plug it in here, because that's the derivative that we have going on, okay? So we know that the bottom, can we agree that the bottom is always going to be positive? Okay, always positive. So we just need to figure out what's happening up top. So if we stick in -2, -2 to the 5th is 32 times 4. So that's negative, so f prime of -2 is -128. Plug in -2 there, and that's going to be -8, but I'll make +16, and plug in a -2 there, and that's going to give us a +4. So big numbers here, but all we care is that it's going to stay negative. Does everybody agree that it's going to stay negative? Good? Okay, now here's the dealio. We cannot make the assumption that the next one is going to be positive. Okay, I know it would be nice, but you can't make that assumption. So we actually have to take a number that's in that little interval. And the worst thing about it is it's a fraction, right? So when we go to do this one, maybe 0.5. So we're going to take the derivative of -0.5. Now remember, the bottom always positive, so we're only interested in what happens in the top. So if we go 4 times -0.5 to the 5th, that's -1.125. And then 2 times -0.5 to the 3rd is plus, right, 0.25. And then this will be +1, right? Put in a 1/2 there, and that'll be +1. Okay, so what actually happens here is we end up with, oops. I guess we don't really need to calculate it out, but might as well. Minus 0.125. So we end up with +625, which again, all we really care about is that it was positive. Okay. All right, now we move to the next interval, and we've got a positive 0.5 in that one. So if we go the derivative of a positive 0.5, now the nice thing about the positive 0.5 is all it's going to do is switch the signs on here, right? So we're going to have a plus 0.125 minus 0.25 minus 1, right? The only thing that's changing is the signs, which definitely means this is going to be negative. Not -1, but negative. And then finally, if we were to take 2 and plug it in here, if we put in a +2, that's going to be so huge that it's going to offset these guys, so that's going to be a positive. Okay, so yes, if you do an ugly one, it is a bit bigger and trickier to do, okay? So then we've got our last section over here, the increasing and decreasing. So this graph from -∞ to -1 starts out by being decreasing. Everybody agree? Then at -1, it flips and it goes to increasing. Then from 0 to 1, it's back to decreasing. And then finally, from 1 to infinity, it is back to increasing. Okay? So this graph does flip back and forth, decreasing, increasing, decreasing, increasing. Phew! So that's a lot of work to get through to do that. Okay? So if we're going to do all this work, we want to take it one step further. So these critical values that we're talking about, we had 1 at 0, 1 at 1, and 1 at -1. They tell us that something special is happening there. Now, we got the critical value of 0, we got that guy from the bottom of the original function, right? Which means that at 0, what is happening? Okay? So we didn't get that from the derivative, we got that because there is a discontinuity, and it's actually an asymptote, isn't it? So at x equals 0, there is an asymptote. Now, we got the 1 and the -1 from our derivative, didn't we? So that meant that our graph is just changing from increasing to decreasing or decreasing to increasing. So when x equals -1, the graph was decreasing, and then at -1 it turned and became increasing. So even though we don't know what the graph looks like in total, we know right here when x is -1, the graph goes from down to up. So that means at that particular point, that's a low value, isn't it? And we would call that a minimum value. So the graph has a minimum value. Now, when x equals +1, okay, +1 over here, again, we're starting from, on one side of +1, we're decreasing, and on the other side, we are increasing. So what it means is we actually have another minimum value. Okay? So we can tell something about those critical values. We can tell what they actually are. Are they asymptotes? Are they minimums? Could they be a maximum? We can tell what's going on there. Okay? So that's our next step. And we call these guys extrema. So extrema. And we're going to start with the relative maximum and minimum. Okay, so the relative maximum and minimum. So we say f of c is a relative maximum. Let's just be honest, I am not going to write out maximum next time, so hopefully a relative max will work for everybody. So f of c is a relative max if f of x is less than or equal to f of c for all x close to c. Part. The second part says f of c is a relative minimum if f of x is greater than or equal to f of c for all x close to c. Okay, so I always hate to erase all our hard. We'll go over these. Okay, so let's just do an example that doesn't actually have a function attached to it. So let me just draw something in here. Okay, so let's say we had something that looked like that. Okay, so do you see that as we're going from left to right, that we start increasing, then we have a little bit of decreasing, then increasing, then a little bit of decreasing, and then increasing again. So there's lots of changes here between increasing and decreasing. And every time we make one of those changes, we have that critical value. Okay, so in this one, there are 4 critical values going on. Okay, now, the idea behind being a relative maximum or a relative minimum is that it's not going to be the absolute maximum of the whole entire function. This function doesn't actually even have a maximum because with that arrow going on and on forever, that means that it continues to grow forever and ever. So there is no actual maximum, but there are a couple relative maximums. So think about zooming in on just this part of the graph right there. When you look at just that part of the graph, is that value a maximum compared to all of the values around it? And it is, isn't it? So we call this a relative max. Now what would this guy be? Okay, so as you zoom in on just the values around it, it is the smallest value compared to the guys around it. So this one would be a relative minimum. Okay, then up here, now we're going to have to zoom in even tighter, but here we have another relative max. Okay. And now here we have another relative minimum. Now, this relative minimum, there's even something more special because we have a relative max over here, but this guy's higher than it, isn't it? So if this is a maximum, how the hell can that one be a minimum? But that's the idea here, is that we're only interested in what's going on right around there. And right around that point, even though there's points over here, this is a minimum compared to the values right around it. Okay, so that's what we're looking at when it says relative maximum or a relative minimum. It's just what's happening right around the value. Okay, let's see. So let's go ahead and do one of these completely all the way, and we will see what pops out. So this says, if f of x is equal to x cubed minus 3/2 x squared, then the instructions just say to discuss areas of increasing or decreasing. Okay? So here we go. So that's all that gets here. So remember that what that means for us is that we want to actually draw that little table and then put the increasing and decreasing in the different intervals, okay? Now remember that the first thing to do for any function is to look at it originally and see if there's going to be any places where it's discontinuous, okay? So this is another polynomial, even though it's got a fraction here, it's still a polynomial, so I think we're good to go. So what we want to do then is go directly to the derivative. So if we take the derivative there, we'll have 3x squared. Then if we pull the 2 down, it's going to cancel with that other 2, so we have just 3x. Okay. And now we need to find our critical values. So to find the critical values, we take the 3x squared minus the 3x, set it equal to 0. Factor out a 3x, which will just leave us x minus 1 equals 0. Okay. And we end up with a critical value at 0 over here, and another critical value when x equals positive 1. Everybody agree, right? 0 from here, positive 1 from here. So this guy, we have 2 critical values. Okay. Now again, we don't know yet whether those critical values are minimums or maximums, but we're going to figure it all out by making this little table. So we'll make our little interval, and then we'll do f prime of x, and then we'll do increasing, decreasing. Okay, so this one's not as bad as last one because we only have 2 critical values, but still we need to go from negative infinity up to 0, from 0 to 1, and then from 1 to positive infinity. Okay. All right, so the first thing to do is to plug values into the derivative. So we take something on the negative side of the graph, like -1, and we stick it in here, okay? So if we stick it in here, that's going to be positive, and then put a -1 in here, that's going to be positive. So it looks like the graph itself is going to be totally positive on that interval when you look at the negative side of the graph. Okay, now let's look at something like 0.5. Okay, so if we plug 0.5 in there, actually you can even go down here and it'll be a little bit easier. You can go to the factored step. If you plug 0.5 in here, so 3 times 0.5 is 1.5. And then if we plug in 0.5 here, we're going to be multiplying by negative 0.5, right? 0.5 minus 1. So in the end, when you multiply those two guys together, we get a negative number, don't we? Okay. So remember, you don't need to figure out what these equal or anything. We just need to figure out whether they're positive or negative. So whatever way will help to do that, just get it done, basically. And then take any number that's bigger than 1, like 2. And if you plug 2 in here, we're going to end up with a positive. So if we plug 2 in, that would be 4, so 12 minus 6, so it's going to stay positive, isn't it? Okay. Which means that we're going to go increasing, decreasing, increasing. Okay, Now, we still have these two values at x equals 0 and at x equals positive 1, okay, that we need to discuss. So we've looked at the areas of increasing or decreasing, but now, for 0, the graph goes from one side of 0, it goes from increasing, so it's increasing, and then at 0, it turns and goes decreasing. So when you think about that, what does that make up here? Okay, is that going to give us a relative max? And here, when x is equal to 1, look what's happening on either side. So on one side of 1, it's decreasing, 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 and then it turns and goes increasing. So right down there at 1, we're getting a relative minimum. Okay. So what we've done here is we have described the shape of the entire graph. Okay, so we described the shape of the entire graph without ever graphing it or anything. We don't really know what exactly the graph looks like, but we know what's going on and where it's going on, Okay. Okie dokie. So there's the second part to this, which I will record in just a minute, but this would be the first part of this one, and then we'll come back and do the second part. If you want to do them back to back right now, that's totally fine, because they go right together, but I'll do it in 2 parts. Okie dokie, everybody. Good job, and we'll continue on more.